Welcome to the deep dive. You ever have that quiet, late-night thought that just sort of pops into your head?
Oh, yeah.
Are you truly making a decision right now, or are you just running a program that was coded billions of years ago?
Mm.
Today, we are taking a stack of some really intense sources, and we're tackling that ultimate question of, fate versus free will, the philosophical challenge of determinism.
It's the mission that really underlies all of physics and philosophy, right?
Yep.
Trying to prove or disprove the very nature of causality.
Right.
Classically, we had this idea of Laplace's demon, this entity that knows the position and momentum of every single particle in the universe.
And so it can predict the future perfectly.
Perfectly.
Yeah.
But today we're seeing how quantum mechanics and cosmology either, absolutely obliterate that view or, and this is the surprise, find these radical new ways to bring it back.
And that's our deep dive mission. We are exploring the extreme edges of modern physics. We'll look at theories that try to restore perfect causality at the quantum level.
And then we'll flip it. We'll look at theories that say time is an active, creative process, something genuinely being written moment by moment.
The core tension here, it seems, is that standard quantum mechanics, the physics that governs everything at the smallest scale, it has this fundamental randomness baked into it.
It does, but so many brilliant minds just cannot accept that randomness is truly fundamental. They argue that the noise we see just means we don't have the full picture.
So we're navigating between those who try to eliminate uncertainty entirely and those who, embrace it as the very foundation for an open future.
Okay, so let's unpack one of the most intellectually compelling efforts to restore that perfect determinism, the de Broglie-Bohm theory.
Also known as pilot wave theory.
Right.
Or Bohmian mechanics.
Right. It's basically a deterministic rival to standard quantum mechanics.
That's it. And the core idea here, it radically changes what we think a particle even is. Standard quantum mechanics says a particle is this, this sort of smeared out cloud of probability.
Yeah, not really in any one place. Exactly. But DBB theory says no. It says that in addition to that wave function, particles have an actual, a well-defined position.
At all times.
At all times, even when we're not looking.
Okay, so the particle is always definite. It's definitely somewhere. If that's true, then why do all our experiments show this uncertainty, this probability?
Because that particle's definite movement is guided by something else. The wave function, which in this theory they call the pilot wave, or the quantum field.
The pilot wave, I like that.
It evolves deterministically, following the Schrödinger equation, and it acts like a kind of invisible compass telling the particle exactly where to go. There's a guiding equation.
So the particle is the thing we see, but the wave is what's guiding its journey.
Precisely. And this gets rid of the infamous measurement problem, which is the biggest headache in standard quantum theory.
The biggest headache, exactly. Because if the particle's position is always real, there's no fuzzy cloud that needs to suddenly
collapse.
Right, no magical collapse when we look at it.
And this is where the theory becomes really powerful for its supporters. Think about, say, thermodynamics. It's based on statistical rules, right? Like pressure and temperature.
Sure.
But those rules emerge from the absolutely deterministic, non-statistical motion of individual molecules. From classical mechanics.
So you're suggesting quantum mechanics is like that, a statistical theory that comes from some deeper deterministic reality.
That's the argument. The familiar statistical rule in quantum mechanics, the Born rule, which tells us the likelihood of finding a particle somewhere, it's not a fundamental starting point in DBB theory.
It's not a postulate.
It's not a postulate, it's a theorem. It's mathematically derived. And it emerges naturally if the system is in what they call quantum equilibrium. They basically argue that the uncertainty we see is just because we haven't found a way to measure the actual position of the particle. The pilot wave is the hidden information.
But okay, as always in physics, fixing one problem seems to create another one. If you restore determinism this completely, you introduce a highly controversial cost.
You do, and it's a big one, non-locality.
Spooky action at a distance.
That's the one. In the real world, physics deals with multi-particle systems. And in DBB, the velocity of any single particle is instantly dependent on the position of all other particles in that system.
No matter how far apart they are.
Doesn't matter. The guiding wave carries these faster-than-light connections. It's overtly non-local.
That's the phrase Einstein hated. And we know this concept is real. I mean, it's what inspired John Stuart Bell to prove his theorem. The experiments later confirmed it.
They did. So DBB offers this beautifully deterministic picture, but it demands an instant connection across the entire universe, and that immediately clashes with Einstein's special relativity.
Which says nothing travels faster than light.
Exactly. To make it all work, you have to introduce a kind of universal now, what physicists call a preferred foliation of spacetime. And that's a major compromise just to keep determinism.
That concept of a universal now, it brings us right to the biggest question in cosmology, which is the nature of time itself. Because if determinism is true, then our future is just set. It's sitting there in a four-dimensional block of reality.
And that perspective is the mainstream view that emerges from Einstein's relativity. It's called the block universe.
Right.
In relativity, time isn't a special river that flows, it's just the fourth dimension, like height or width. So if you view reality as this four-dimensional object,
The past, the present, and the future all exist together.
they all coexist equally. It's like a massive movie reel. All the frames are there simultaneously. Our perception of time passing is, well, as Einstein himself said, a stubbornly persistent illusion.
I have to say, I find that thought deeply unsettling. I mean, if the entire future is already laid out, then your choices, what you eat for breakfast tomorrow, who you vote for in 10 years, it's already done.
That's the philosophical consequence. And cosmologist George Ellis, one of our sources, he argues that if the block universe is literal, it just wipes out free will, it wipes out moral accountability.
Yeah, that famous quote about Hitler.
Yeah, he said if the future is fixed, then Adolf Hitler had no choice to other than what he did. And Ellis finds that conclusion, morally and practically untenable.
So he offered a way out, his evolving block universe.
Yeah.
How does he keep time as a dimension but make the future unwritten?
He just tweaks the boundaries. So the past and the present, they're fixed, they're set. That's the solid existing block.
Okay.
But the future boundary is not fixed. The present is literally the leading edge of space-time crawling outward moment by moment. It's constantly transforming potential possibilities, the future, into fixed events, the past.
This sounds much closer to how we actually experience life.
Yeah.
That we're creating the future as we live it.
Precisely. And Ellis insists that quantum uncertainty, which we'll come back to, is the key evidence. He says, quantum uncertainty, to me, says the future is not determined until it's happened.
It provides the genuine randomness.
It allows the evolving block to expand into genuine novelty.
Now, before we jump back to quantum mechanics, there was one more mind-bending idea about time, Joan Vaccaro's theory.
Yes, T violation. The idea that the flow of time itself might not be a fundamental feature of the universe. It might just be a result of a subtle cosmic imbalance, a violation of time reversal symmetry.
Meaning the laws of physics don't work exactly the same forwards and backwards in time.
Right. And Vaccaro suggests that dynamics itself, the change we see, might just be a consequence of this tiny asymmetry. It's very abstract, but it reinforces the idea that the direction of time isn't arbitrary. It's baked into reality.
Which fits nicely with Ellis's idea of an expanding block.
It does.
Okay, let's circle back to the quantum sorts of this indeterminism that Ellis relies on. If the Bohmians want to get rid of it, where does genuine uncertainty actually live in the traditional view of quantum mechanics?
It lives in the moment of observation. In standard quantum mechanics, like the Copenhagen interpretation, time evolution has two very distinct modes.
Two different ways things can change.
Yes. First, you have the U process. That's unitary evolution. This is the smooth, predictable evolution of the wave function, that probability cloud according to the Schrödinger equation.
And that part is completely deterministic.
Perfectly deterministic, but then
Something goes wrong when we look at it.
that's the second mode, the chaotic part. The R process, reduction. This happens during measurement. When you open the box to check on the particle, the R process kicks in, forcing the wave function to collapse instantly into one single definite state.
And that collapse is where the randomness comes from.
That's it. It's inherently probabilistic and non-deterministic. It's what introduces genuine randomness into the universe.
So it's like the universe is deterministic right up until the point you interact with it, and then it just, throws a set of dice.
Exactly. And because that randomness seems so unsatisfying to so many, other interpretations try to eliminate that R process. The most famous one is the many worlds interpretation.
Ah, the one where infinite versions of us are splitting off every second.
That's the one. Many worlds completely gets rid of the R process. A measurement isn't a collapse, it's just entanglement. Whenever an interaction happens, the entire universe splits. The wave function of the universe as a whole is perfectly deterministic. It's evolving smoothly, but the observer is duplicated and experiences only one random outcome. For every choice you might make, a world exists where you made it.
So the universe is deterministic, but my experience isn't, because my consciousness just follows one random path through this constantly branching multiverse.
I love that quote where critics of DBB sarcastically called them, what was it?
Parallel universe theories in a state of chronic denial.
Yes, because DBB also has these non-interacting empty branches of the wave function.
It captures the complexity perfectly. But okay, if you don't like many worlds, and you don't like the non-locality of DBB, you can follow Roger Penrose. He argues that the collapse of the R process, it must be a real, objective, physical event.
Caused by something more physical than just consciousness looking at it.
Exactly. He calls it objective state reduction.
And that leads us straight to the most audacious theory yet. The one that tries to link quantum mechanics directly to human experience and maybe free will, orchestrated objective reduction. ORCH, or R, from Roger Penrose and the anesthesiologist Stuart Hameroff.
Right.
ORCH-OR is the ultimate attempt to find a physical basis for consciousness, suggesting it originates not in complex classical neural networks, but at the quantum level inside our neurons.
And the reason Penrose thought a quantum mechanism was required, it goes back to math, right? Gödel's incompleteness theorem.
That's right. Penrose argued that human mathematical understanding and insight must be non-computable. It requires a non-algorithmic physical process in the brain.
And he thinks objective reduction is that process.
He does. He proposed that objective reduction, or OR, is that non-algorithmic process. He suggested that superposition states have gravitational self-energy, and these massive superpositions spontaneously collapse when that energy hits a certain threshold.
Okay, so they just collapse on their own.
Yes, and crucially, the state the system collapses into is selected non-algorithmically. It's influenced by what Penrose calls non-computable information, embedded in the very structure of space-time at the Planck scale.
Wow, okay. And then Hameroff came along and supplied the location for this process.
He did. The microtubules within the neurons, he hypothesized these tiny scaffolding structures are where oscillating electrons in their proteins, called tubulin, form quantum bits, qubits, which then orchestrate the collapse.
The theory is very controversial, but it has recently sparked some really specific experimental results that are hard to ignore.
That's true. Studies have confirmed superradiance, a collective coordinated quantum optical effect in large networks of tryptophan molecules,
Which are found in microtubules.
which are abundant in microtubules. And this effect was seen even in a warm, noisy environment where quantum coherence was long thought to be impossible to maintain.
This is critical, because the brain is the definition of warm, wet, and noisy. Finding quantum effects there is a huge theoretical boost for ORCH-R.
And the evidence gets even more compelling when you look at anesthesia. Simulations of tubulin found that anesthetic gases abolish a specific collective oscillation peak at 613 terahertz, which Hameroff ties directly to conscious processing. And another study showed that stabilizing microtubules with a drug called apothelone B actually prolonged the time it took for rats to lose consciousness under anesthesia. It suggests a direct physical link.
Okay, here's our critical thinking moment. These results sound fantastic for the theory, but what are the scientific counterarguments?
Well, first, the general physics criticism is still there. Most physicists argue the decoherence risk is just too high. A quantum system won't stay coherent long enough in a cell to do anything meaningful.
Right.
But the second, very specific criticism is about that experimental work on superradiance.
The one that sounded so compelling. What's the flaw?
The problem is biological feasibility. The researchers achieved superradiance by doing the experiments in an artificial environment that excluded proteins that are naturally found with microtubules. Specifically, they excluded a protein called ferritin.
And what does ferritin do?
Ferritin is known to interact with microtubules in living cells, and critically, it's known to quench superradiance. It stops it.
Wait, so the experiment that showed quantum coherence was possible in a noisy environment. It worked because they removed the one thing that would naturally stop that coherence in a real neuron.
That's the key critique. If you remove the natural quenching agent, the result, while valid in the lab dish, may not reflect neuronal reality at all. And that casts some serious doubt on whether ORCH or R could actually survive inside your brain. So if we synthesize this whole journey we've been on, we have interpretations like de Broglie-Bohm that they eliminate quantum probability entirely.
Right. They assert a set but non-local destiny.
Yep.
Your future is already written, even if the writing is spooky.
It is spooky. And then we have cosmologists like George Ellis and theories like Orkoar, which embrace quantum probability and genuinely objective collapse.
As the foundation for an open, unwritten future that's being actively created by chance and by choice.
And what's at stake here is truly profound. I mean, these aren't just academic puzzles for physicists, are they?
Not at all. They define whether the choices you make, from, profound ethical decisions to what you have for lunch, are just inevitable links in a chain that was forged at the Big Bang.
Or if they are truly creative acts, introducing genuinely new information into the world.
And if you still find that idea of a fixed reality compelling, it's worth remembering the intuitive human resistance to the block universe. George Ellis channeled that feeling so well when he quoted Omar Khayyam.
The moving finger writes, and having writ, moves on.
Nor all thy piety nor wit shall lure it back to cancel half a line, nor all thy tears wash out a word of it.
The deterministic view says the entire script is finished, and the moving finger is just tracing lines that are already there. The open universe view says the finger is truly writing something novel right now.
So we'll leave you with this to think about. What evidence would it take for you to switch sides on this? And if the future isn't fixed, how much potential agency do you truly possess?